What do a light bulb, a washing machine and a toaster have in common? Are you still thinking, hey, their common link isn't something magical, it's just that they are all powered by a form of energy called electricity. Hi, I'm Arjun Bhagat and welcome to Topper's Exam Special. Today we are going to prepare the chapter Current Electricity for the board examination. But before we begin learning the concepts, it is important for us to know the weightage of this topic and the general trends that are being followed in the examination. So let's take a look at our first segment, Trendspotting.
The chapter Current Electricity has been assigned 7 marks out of the total 70 marks, which is about 10% of the total physics paper.
Now that we know what to expect in the exam, let's recall the topics covered in this chapter. So let's do a quick recap.
In this chapter, we learnt about resistance and resistivity. Then, we did drift velocity and relaxation time. We also did Kirchhoff's law. Then we talked about meter bridge. And last but not the least, we learnt about potentiometer.
It's going great only if you say you covered all of it. You know, it's really important to have your basic theory clear in your mind, and if you know your theory well, that's half the battle won. Now let's take a look at our next segment, Knowledge Dip, where we tell you what ability you require to win the rest of the battle.
Well, questions from this chapter test all your abilities. So you need to sharpen your conceptual, numerical, knowledge and representative skills to score full on full in this chapter.
Well, once you have all these skills in place, don't get overexcited. Remember to be patient and focused always. So with all that patience and concentration, let's take up a model question.
This question is divided into 2 parts. Here you need to state Kirchhoff's rules in an electrical network. Using these rules, also determine the value of the current I1 in the electric circuit you can see on your screen. It's a 3 marks numerical. Our difficulty meter rates at average. Let us now solve the problem. Kirchhoff's rules for electric network are junction rule, which means at any junction, the sum of the currents entering the junction is equal to the sum of currents leaving the junction. Then, loop rule, which means the algebraic sum of the changes in potential around any closed loop involving resistors and cells in the loop is 0. While applying Kirchhoff's loop rule, the EMF of the cell is taken as positive if the direction of traversal is from its negative to the positive terminal, and taken negative if direction of traversal is from its positive to the negative terminal. Similarly, while applying Kirchhoff's loop rule, the IR product is taken as negative if the resistor is traversed in the opposite direction of assumed current, and taken positive if resistor is traversed in the same direction of assumed current. By Kirchhoff's rule, current I1 plus I2 is equal to I3. Applying loop rule to both the lower and upper loops, we get, for upper loop, 40 I3 plus 20 I1 is equal to 40. For lower loop, 40 I3 plus 20 I2 is equal to 120. Adding the equations of lower and upper loop, we get 80 I3 plus 20 times I1 plus I2 is equal to 160. But I1 plus I2 is equal to I3, hence 80 I3 plus 20 I3 is equal to 160. By solving, we get the value of I3 is equal to 1.6 ampere. Again, by putting the value of I3 in upper loop and solving, we get the value of current I1 equal to minus 1.2 ampere.
Well, practicing questions is very important because it's a process through which you remember important concepts and develop critical skills. So let us begin preparing for the exam with our first practice question.
You need to explain why the resistivity of a metal increases and that of semiconductor decreases with rise in temperature. This is a moderate difficulty conceptual question worth 2 marks. Here, resistivity of material is given by ρ equal to m by n into E square tau. We see that in metals. As the temperature increases, the thermal speed of electrons increases. Free electrons collide more frequently with the positive metal ions. The average relaxation time decreases. Consequently, the resistivity of the metal increases. Another mark will be added here if you write this correctly. And in the case of semiconductors, the number density n of free electrons increases with temperature. As a result, the resistivity of semiconductor decreases with the increase in temperature. Now, if you mention this as well, you get 1 more mark.
As the examination period is approaching, you might be pressurized, but don't worry, we have more practice questions that will help you get rid of this pressure, because if you prepare well in advance, then even pressure can't pressurize you. So let's move on to our next practice question.
The question says that if 12 cells, each of EMF 1.5 volt and internal resistance 0.5 ohm, are arranged in m rows, each containing n cells connected in series as shown. So, calculate the values of n and m for which this combination would send a maximum current through an external resistance of 1.5 ohm. This question is a 3 marks numerical, and our difficulty meter rates it as average. In this question, we have 12 cells, each of 1.5 volts, with internal resistance 0.5 ohm, arranged in m rows, each containing n cells in series. The key idea we use is that for maximum current through external resistance R, the net equivalent internal resistance should be equal to the external resistance. The equivalent internal resistance of n cell in series, each of internal resistance R, is NR, and the net equivalent resistance Req of the whole combination of cells having m rows in parallel is R equivalent equal to NR by m. Putting the net equivalent internal resistance equal to the external resistance, we have NR by m equal to R. By putting the value of small r and r, we get n equal to 3m. Again, total number of cells in the combination is equal to nm, which is equal to 12. Solving 1 and 2, we get n equal to 6 and m equal to 2. Hence, there are 2 rows with 6 cells in each row.
So 2 practice questions have been solved successfully. The coming problem is also a numerical one. It carries 3 marks and is moderate as per the difficulty meter. Do not waste time on the figure, make a simple one with proper labels so that the examiner can understand it easily. So let's see what it asks you to do.
The figure you can see on the screen shows the experimental setup of a meter bridge. The null point is found to be 60 cm away from the end A, with X and Y in position as shown. When a resistance of 15 ohm is connected in series with Y, the null point is found to shift by 10 centimeters towards the end A of the wire. You are required to find the position of null point if a resistance of 30 ohm were connected in parallel with Y. As we know, the meter bridge is the practical application of Wheatstone bridge that is used to measure an unknown resistance. Using the balance condition of a Wheatstone bridge, we have X by Y equal to L1 by 100 minus L1, where X and Y are two given resistances and L1 is the length of the wire from the point A to the obtained null point. On simplifying, we get the relation X equal to 3 by 2 into Y. Now, on joining 15 ohm resistance in series with Y, the null point shifts to 10 centimeters towards A. It means L1 equals to 60 minus 10, which equal to 50 centimeters. So, the new position of the null point is 50 centimeters from the end A. Again, applying the balance condition, we get the relation X by Y plus 15 equal to 50 centimeters by 100 minus 50 centimeters. Now, after substituting the value of X from above, relation and simplifying it, we get the value of resistance Y equal to 30 ohm. Again, substituting the value of Y in relation X equal to 3 by 2Y and solving it, we get the value of resistance X equal to 45 ohm. When a 30 ohm resistance is joined in parallel to Y equal to 30 ohm, we get the combined resistance Y dash equal to 15 ohm. Now, if null point be obtained at L dash centimeter from point A, then applying the meter bridge relation, we get the new null point L dash equal to 75 centimeter.
Alright, I do hope you log on to our website www.topperlearning.com, because here you can get every kind of help related to your examinations. Well, though we have more practice question, a HOTS problem and some handy tips for you, we'll take a short break before that, and when we return, you ought to have solved this breaking question. Don't be afraid, it's simple and easy.
The question asks you to give reason for why the electrical conductance of electrolyte is less than that of metals. Before we slipped into the break, I asked you a question. You were required to give reason for why the electrical conductance of electrolyte is less than that of metals. As we know that metals have an exceedingly high number of conduction electrons whose mobility is quite high. In electrolytes, number density of ions is comparatively less and their mobility too is small.
Welcome back, I'm Arjun and you're watching Topper's exam special on the topic current electricity. Well, before the break we glanced through a model question based on Kirchhoff's rules and also solved some practice questions related to meter bridge and resistivity. Let us now proceed with some more practice questions. Here's the next one.
A potential difference of 2 volts is applied between the points A and B, shown in the network drawn in the figure. You have to calculate equivalent resistance of the network across the points A and B and the magnitude of currents flowing in the arms AFCEB and AFDEB. Take a look at the solution. Since the Wheatstone bridge is balanced, current through the central 2 ohm resistance is 0. So, resistance of the arm FCE is equal to 2 plus 2 equal to 4 ohm. Similarly, resistance of the arm FTE is equal to 2 plus 2 equal to 4 ohm. Therefore, total resistance between points A and B can be obtained by applying the law of parallel combination of resistors. Hence, after solving, we get the total resistance between A and B equal to 2 ohm. Current in arm AFCEB can be obtained by applying Ohm's law. So, after putting the value of voltage and resistance, we get the value of current equal to 0.5 ampere. Similarly, in arm AFDEB, we get the value of current equal to 0.5 ampere. The value of current in both the arms is same because potential difference and resistance of 2 arms is same.
I hope you got that one right. And also remember that if your answer sheet is neat, the examiner would become a bit more liberal while marking you. He or she would actually be very forthcoming to check your paper. So on that note, let's take a look at the last practice question of the day. We'll then be ready to take up the difficult challenge, the HOTS question. So solve this one quickly.
Here we are shown the plot of the variation of potential difference across a combination of 3 identical cells in series versus current. So, what is the EMF of each cell? Let's see how to solve it. The key idea is that in open circuit, when no current is being drawn from the cell, the terminal potential difference is equal to EMF of cells. From the graph you can see that when current is 0, EMF is 6 volts. So, this is the EMF of the combination of cells. And EMF of each cell is equal to 6 volts by 3 equal to 2 volts. Thus, you score 1 mark.
I hope you enjoyed solving the questions. Now it's time for the HOTS segment. This section was introduced by the CBSE in 2008. At Topper, we prepare you for every challenge. So when we talk of high-order thinking skills, we expect you to get this one right. Take a look.
Here you need to define the term potential gradient of potentiometer. In a potentiometer arrangement, a cell of 1.20 volt gives a balance point at 30 centimeter length of the wire. This cell is now replaced by another cell of unknown EMF. If the ratio of the EMFs of the 2 cells is 1.5, calculate the difference in the balancing length of the potentiometer wire in the 2 cases. This is a 3 marks numerical. It is rated as moderate on the difficulty meter. Try it. Let us now solve it. Potential gradient of a potentiometer is defined as the fall in the potential per unit length along the given potentiometer wire. If V be the potential difference across a length L of the potentiometer wire, then potential gradient is equal to V by L. This definition gives you 1 mark. In present problem, it is given that ratio of 2 given cells is 1.5. As we know, EMF of first cell is given by E1 equal to K times L1. By substituting the value, it comes out to be 1.20 equal to K into 30 centimeter. This is equation 1. Now, E2 is equal to K times L2. But also, we know that E2 is equal to E1 by 1.5. By substituting the values, we get the value of L2 as 20 centimeter. Another 1.5 marks are added to your kitty if you get this answer right. So, the difference in the balancing length of the potentiometer wire in the two cases be L1 minus L2 equal to 10 centimeter. So finally, you are rewarded the remaining half a mark for this.
I know you took the challenge well, but do visit our website www.topperlearning.com and take up more such challenges. This website provides a wealth of study-related information and exercises to help you become a successful and independent student. Well, now let's take a look at the tips for the day.
While applying Kirchhoff's loop rule, the EMF of the cell is taken as positive if the direction of traversal is from its negative to the positive terminal, and taken negative if direction of traversal is from its positive to the negative terminal. Similarly, while applying Kirchhoff's loop rule, the IR product is taken as negative if the resistor is traversed in the opposite direction of assumed current, and taken positive if resistor is traversed in the same direction of assumed current. And for maximum current, the external resistance must be equal to the total internal resistance.
I hope today's learning was fun and that you enjoyed every bit of it. As it is said, practice makes you perfect, so keep practicing more and more questions. It's now time to wrap up this episode. See you next time with another episode of Topper's Exam Special. Till then, good luck and have fun.